So I'm in chemical engineering at University of Rochester. This is sort of a long title. I'm basically going to talk to you about how we can do sort of small data learning. So how do we work on machine learning when we don't have a ton of data? And we do that with physics-based models. Okay, so I thought I'd put a quote about interpretability. All right, this is just meant to be provocative here, but it is easier to teach physics to learn with machines than to teach machines to learn physics. So the idea of my talk is that basically we're going to try to teach physics to learn from data rather than trying to teach machines to learn physics. Okay, so the idea is we're going to start with physics-based models and develop methods like used in machine learning to make them better with data, rather than try to start with machine learning methods and teach them physics. Okay, so that's sort of a And why? What does it do with interpretability? Is that we are really good at interpreting physics-based models. Like if I have the output of a physics-based model, I know I can take a radial distribution function, or I can look at some kind of collective variable. But then when it comes to machine learning, people don't really know how to interpret it. So I would argue for interpretability purposes, it's actually a smart idea to start with physics-based models. Okay, so this is sort of like a high-level idea. I have a student who worked with me over the summer. She's an artist, and so she took a stab at making our own iterative molecular design figure. So this is ours. So what I'm going to talk about today is how do we do all of these steps together. And the way we can be small data learners is that we choose which experiments to do well, and we have a physics-based model at the top. Think of a slide, yeah. So we have a physics-based model at the top here, and so these work well at transferability and prediction, and then we use deep learning on the bottom for choosing which experiment to do next. Okay, so down here we'll talk a little bit about deep learning. Okay, so I just thought that we could put a few of the highlights here. So here's iterative molecular design from some other people. I'd like to have a collection of these, so if anybody has their own, please don't be afraid to send them, and I'll put your name up on the list for iterative design. And everybody sort of has the same idea, so there we go. Okay, so how do we actually do this? So in my talk, we'll talk about 3 different areas. So we're going to talk about using maximum entropy methods to take experimental data to improve a model. I'm going to call my physics-based model a latent model sometimes because it has extra structure you don't really need to be predictively accurate. So how do you take experimental data and add it to a physics-based model? Then I'm going to talk about how do you take a physics-based model that has a maximum entropy built into it and turn it back into a regular physics-based model. So we're going to do derivative-free optimization there. Then how do you take a predictive model and then generate hypotheses? So if you can say whether a molecular structure is good at how a molecular structure has some kind of activity, can you generate a bunch of molecular structures to try in your model? So I put this as a free space because there are tons of methods, and I just use what's available. So I don't try to innovate in there. I don't think about it, and I think people are doing great work, so thank you, everyone. And then the last one I'll talk about is if you have sort of a list of candidate experiments, how do you choose which one is the best? So not just generating them, but how do you choose which one's the best? Okay, so that's what we'll talk about in this talk. Yeah. So I'm going to say the word physics-based model. When I say physics-based model, I mean a computer simulation from something with a Hamiltonian. I'm going to say the word observable. That just means something that you can measure in an experiment and corresponds to an ensemble average. So the position of atoms, or these density fields we saw yesterday at a given slice, that's not what we're looking at here. We're talking about an ensemble average, so the average over a bunch of frames, or the expected value. That's what we're thinking about when we say observable. And when I say the word latent, I just mean the stuff that is not an ensemble average, that's extra structure that we don't really need. So where all the atoms are, what the conformations are. Okay, so this is a simulation. Okay, so if we have 2 atoms, we maybe know how they interact well from quantum mechanics, or this is the Lennard-Jones potential, and then sort of a simulation is where we take how those 2 particles interact and run basically a movie of it. So we use Newton's laws of motion to propagate this knowledge of how atoms interact to generate a simulation. So although they look cool, there are other reasons to do this. One of them is that if we know the position of every atom, by doing a simulation, we see the atoms according to their probability from the Boltzmann distribution. So every time we see an observation in our simulation, that's sampled according to the Boltzmann distribution. So if we just take a numerical average of anything, that is the ensemble average. And so to put this in a slightly more mathematical way is that the probability of seeing some conformation in a simulation that's a Hamiltonian simulation, and I'm neglecting velocity, is just equal to the basically the Boltzmann factor for each conformation. Of course, there's some normalization. And then if we have all of the positions of the atoms and we know the probabilities from doing a simulation, we can compute the ensemble average of anything. And that corresponds to what we would observe in an experiment. So that could be something like the NMR chemical shift, or that could be the free energy of activation of something. Okay. So people are great at this. Molecular dynamics is a good tool. People use many different ways to simulate from these potential energies. But how do you actually improve them when you have an observation that contradicts it? So that is, how do you take these potential energies and modify them after you have an observation from an experiment? So I'm going to motivate this with an example. Okay. So we're going to talk about quantum dynamics of water. Like the last speaker had mentioned, quantum dynamics of water is confusing. But one of the things for why we need quantum dynamics of water is observing proton transport. So if you know anything about chemistry, you know an acid-base, basically the proton is what governs acid-base chemistry, and whatever 90% of biology is acid-base chemistry, as some people say. But it turns out that acid-base chemistry, that proton moving through water, is actually having bonds breaking and reforming. So protons moving through water is actually a chemical reaction happening over and over again. And that's called the Grotus mechanism. So the Grotus mechanism is that when you have an excess H, an excess proton, a hydrogen atom with no electrons, and it's moving through water, what happens is it's breaking bonds with water and then reforming bonds with water. And that's how it moves. And that's a really common mechanism. But there's another way it can move, is it can just sit on the water and the water itself moves. And that's sort of the classical way that protons move through water. And if you just do a classical simulation, you'll be off by 40 or 30% for predicting proton diffusivity in water. So this is a really wonderful example of why you need quantum mechanics simulations of water. Because if you go do classical MD of water, you can get a lot of good properties. But proton diffusivity is not one of them. Okay, so we'll just watch a movie. So this is a quantum dynamics simulation of water showing the Grotus mechanism. So let's see if this works on a movie. Yeah. So this is my hydronium here. So this is the oxygen which has an excess proton. And so you can see that there's bonds breaking and forming here. Oh, we got to find it. Where did it go? Oh, this one has the excess proton. Oh, now it's giving it back. Okay, so you see that the proton is moving, not by actually moving, but it's hopping between waters. So the extra proton moves from water to water. Okay, great. So by the way, this is 100 picoseconds, 128 water molecules, I don't know, 250,000 CPU hours or something like this. And this is matches the mechanism correctly. So this is probably the most accurate water simulation of proton diffusivity you'll see today, I can guarantee. Yeah, I like to watch it because it took a lot of work to make, but it's on YouTube if you guys want. All right. Okay, so what is actually numerically the problem? Is that in experiments, we see a ratio for the Grotus mechanism to the vehicular mechanism of 4:1. But then if we do DFT, just normal BLIP DFT, well, I shouldn't say normal, there's a little bit of work on this. But when we do quantum dynamics of water, we get a 70:1 ratio. So DFT of water is highly overstructured. And because DFT of water is highly overstructured, it's really easy to have protons hop from water to water. So it forms a nice tetrahedral geometry, so water can accommodate these extra protons. Now, just because of a cancellation of errors, it turns out the proton diffusivity is not bad. See, it's 0.93 angstrom squared per picosecond in experiments, and it's 0.54 in DFT water. So you might think you're doing well, but the reason that you're doing well is because your water is basically stuck in place at 300 Kelvin, and then you're having these protons hop from bond to bond. So you have completely the wrong mechanism. So it's both qualitatively inaccurate and quantitatively inaccurate. Okay, so even if you use a dispersion correction, you improve this a little bit, you get within maybe 1 order of magnitude almost of the right water diffusivity, and then you get a little bit closer to the proton diffusivity. Okay, so DFT of water is a really hard system to find out how to improve your model, right? You could change your basis set, you could change your cutoffs, you could change your dispersion correction. You could change your temperatures, what some people do. You could change your pseudopotentials. You can change your functional. So there's all kinds of things to change. And it's not obvious which one should be changed. Okay, so the question is, if you know your system is wrong, how do you improve it with this experimental data? Like, rather than just look at this number and be like, oh gosh, we're wrong, how do we change the model to match that? Okay, so that's this is the crux of the talk. So we do something called small data learning. So we'll return. Don't worry, we're going to fix quantum dynamics of water. But for now, we're going to talk about how we can actually accomplish this. So the idea is that we want to start with an approximately correct model, DFT of water, for example, and we want to bias it to be experimentally consistent. Now, there are many ways we can change quantum water to work, and people have done this. Actually, one of the most common ways to fix quantum water is just raise the temperature to 330 Kelvin. So if you want to study room temperature water, you just raise the temperature to 330 Kelvin. It's confusing, I know, but it works. And so there is a large sort of space of ways you can change your model to be experimentally consistent. So what I'm going to argue today is that one way we can make that choice to make it unique so that there is no ambiguity in how we change our model is to add an extra constraint or an extra optimization, is that we're going to find how to bias our model with the shortest entropic distance. Okay, so we have an idea of distance, and that allows us to sort of find a unique way to change our model to match. Okay, so this is a very general idea. And this is all based on probability. So if you're doing a simulation, usually you're sampling from a probability distribution in almost all cases. So here we have a probability distribution, P naught. We want to find a P in this space of permissible, experimentally consistent probability distributions. So this means that the ensemble average of all of these models is correct. So that would be like the diffusivity of water is correct. So this is a nice, easy problem here. We have a constraint that we need to satisfy, and we have a distance. We're using I'm just going to call it KL divergence because I always forget how to say that. Kubler-Leibach or something divergence. And so that's our measure of distance. And so we have basically a constraint, and we have a minimization criteria. And so we can just use Lagrange multipliers. The only confusing part is that it's Lagrange multipliers with functionals instead of scalars, but that's fine. It can be done. So, lots of people have done it. So here's some people who've done it. And so it turns out that the way to minimally change your ensemble is to add a term that's e to the minus alpha f of x. Okay, so if this is my original model, the minimal change I can make is to add this exponential term here. What that means for the potential is that if this is my original potential here, I'm adding a linear term to my potential energy with a scalar alpha. Okay, so the smallest way to improve your model is to add a linear term to the potential energy that's linear in your observable. Now, I didn't say how do you make it match the experimental data, right? That's the thing, is that this alpha here, you have to choose alpha so that you match the constraint. So in some sense, we've made no progress, right? We just basically said we want to match the constraint, so we can add this extra term that is linear in the potential energy, and then we now need to scale it so that we match the constraint. Is there a question? Oh, crap. Shoot, I lost it. Yeah, so it's R. Okay. Pretend this is R. Yes, that's R everywhere. Okay, so that's the first sort of conclusion from the maximum entropy method, is that the smallest possible change to your model is to add a linear term in the observable. Okay, so I'm not going to go into this, but obviously it's minimal. I just made an argument for that. It's also unique. There is a unique solution. So we went from having all these possible ways to change it, but it's also unique. Now it's mathematically unique. As of 2017, there were 28 competing minimal biasing methods, and my method is one of 28. I think there's probably now 50 minimal biasing methods. So this idea of maximum entropy biasing is actually getting very popular. And a lot of people have different ideas about how to approach this. So you could do Bayesian instead of maximum entropy. You could do maximum parsimony, minimum parsimony, I forget. There's a lot of different approaches to this. So here's what this looks like. So if I had a probability distribution, so I have here in blue the unbiased probability distribution, and I have my observable. Remember, our observables are averages. So I'm just taking the expected value of x. So this is the average of x. What I'm showing in green is that if I observe a piece of data which says my average should be here, the green is the smallest possible change to my probability distribution I can make. Okay, so you see, like when the green line is near the blue line, it almost looks the same, right? So we're making the smallest possible change to match our new piece of data. And the way it works is there's this alpha term. In this alpha term, there's one alpha for every possible piece of experimental data. So when we get a new experimental data, we get the alpha for that, and then now we have our minimally biased probability distribution. Okay, so minimal and unique. All right. So how do you actually find alpha? So with any kind of machine learning optimization method, so you can use stochastic gradient descent. We use follow the regularized leader, which is basically a variant of stochastic gradient descent. And you need to have a gradient to follow. The gradient, it turns out, is this. And what's beautiful about this being the gradient is that because inside of our potential energy we have the observable itself, the gradient doesn't involve the potential energy at all. Because the only term that actually survives the derivative is the observable itself. So the covariance of the derivative is the gradient. So that is a really fascinating conclusion, that because we're putting our observable back into our probability distribution, so one of the terms in our probability distribution is the observable, then when you take the derivative of the probability distribution with respect to the observable, you only get the observable left. So it turns out that it's a very nice, easy computation. So you can actually implement this in any simulation engine easily, because you're not actually trying to do some kind of bookkeeping where you see how the potential changes as your observable changes. You just compute the variance of the observable. And then you can implement this in any simulation engine where you compute an observable. Okay, so back to water. Okay, so what is an experimental piece of data in water? So one of the things we can look at is the radial distribution function, or pair-pair correlation function. And I didn't know anything about astrophysics, but I think it's somehow related to the power spectrum, I think, maybe. So the radial distribution function is the probability of finding another particle as a function of distance from any given particle. So in water, that's our quantum dynamics of water, is this red line. It's very peaked, which means there's a lot of structure. Water is overstructured. So in experiment, we know water is not overstructured. Water is a liquid, so doesn't have all this structure, just has some short range structure. Okay, so then what we're going to do is we're going to take this data from synchrotron X-ray scattering, and we're going to use it in our DFT model explicitly. So here we go. So I did this method. I did the follow the regularized leader on my alpha term, and I found the minimal bias to change my DFT of water and the nuclear coordinates. And then now you can see my RDFs match very well. So this is where we started, and then now this is where we are. Now this is not surprising, because I just said that we can find a unique minimal bias to the RDF, right? So obviously our RDF is going to match. Now one thing you might wonder is that when I presented all the math, it was all with scalars, right? But this is not a scalar, this is a function. All we do is we just take features of this. So we just take moments of it. We do integrals with different kernels. So you can see we match it. I mean, that makes sense though, that's what we wanted to match. But what we wanted to do is see for other properties which we didn't bias, did they either improve or stay the same? Now remember, the whole hypothesis here is that we want to minimally change the model, which means if everything stayed the same, that would be ideal. But if things do change, we want them to just improve a little bit. So here we go. So we started in the dashed line. This is the purple one, and this is the experiment. So we improve a little bit, right? So we improve a little bit. And then here we improve a little bit again. Yeah?
Why do you want to minimally improve your model?
That's a great question. Why do we want to minimally improve our model? I will make a philosophical argument, because I believe my model is approximately correct. And I want to be, my model has good properties, like it's got physics, and it's got interpretability, and it usually has transferability, and it's good at extrapolating. So that's why I want to minimally change it. Now you can make an argument that, forget the model, it's approximate, it can just be an initial guess. Then you lose that constraint, and then you could go in any direction.
So it's so different to me. I'm trying to think in a sort of Bayesian sense.
Sure.
You have two models.
Yes.
And you're like, I really like this. I made this model, and other person made
yes.
this model, and I
yes.
like that one twice as much. Right?
Yes.
Sort of, how do you?
So maximum entropy and Bayesian inference are equivalent with certain conditions on your prior beliefs. Okay. So it's like, if you're doing Bayesian inference, you have your prior belief is your model, and so you always keep in that model in your posterior, right? So you could make an argument, why have a prior belief of the model, right? Why not just try to get as good a fit as possible? Well, that's what the difference between Bayesian and likelihood maximization is. Question?
Oh, it's not a question. I could add some statistical point of view.
Yeah, please.
Yes. So the divergence, the entropy that is used, is the geodesic distance in the space of statistical models. So it's like the shortest path in the space of statistical models, and that's what we already know. But it's also a way to say, I want a change that doesn't introduce other artifacts. So if I choose a basis and want to add something in a basis, then you sort of, put your prior belief that that basis is good. Here you don't introduce any basis, so those plus alpha f of x comes directly, it's non-parametric, comes directly from the belief that you want to match that particular expectation. So it's as uninformative as possible. So corresponds mathematically and philosophically to the Bayesian least informed, like totally uninformative. I don't know anything. It's like the
Occam's razor.
It's Jeffrey's prior something. It comes from Maximum.
Yeah.
Right.
Yeah.
And kill that. Yes.
But that's still in the one model case, right? Like if you have two, then if you had two sort of slightly different models, then there's like this geometry between. I mean, I understand what you're saying. That's interesting. But if you have two, then you really have to start like figuring out how to kind of adjudicate between their differences or something, right? Like.
So yeah, this is.
Or is it just the closest point?
This is just showing you how to take an approximately correct model and find a way to improve it. It's not really meant to compare models, although you probably know more than me. Do you have a thought on that?
I couldn't quite follow what you said on the last slide, so
Yeah.
explain what you said on the last slide.
Here?
Oh, no, like
Keep going back or forward?
the last thing you said. No.
Just the last thing I said. Okay.
I was just talking about maximum entropy.
Yeah. So.
The exact use.
So we biased this. So we basically added 4 terms to our potential energy that are linear and different features of this. So we featurized this because it's a function, so we did some featurization here. And then I was just making an argument that we're changing everything else as little as possible, but it's improving in the correct direction. So this is sort of empirical observation, but we're minimally changing it. But yeah, I don't think that this method is, maybe there's a way to connect it to comparing two valid physics-based models, but I don't know how to do that. But this is sort of like if you have, some model that you like because it's interpretable and physics-based, how do you improve it with data? So maybe, if you're just comparing them, the fit is the way to go. I don't know. Because, you have a guarantee on the degrees of freedom and you have a guarantee on, and you have a minimal change, so.
In particular, maybe in the last slide,
Yeah.
You had an original model, and then you're trying to match onto these features. But
Yeah.
But I can't tell from the axis. But what's stopping you from following this geodesic until you match it exactly? It looks like you're not all the way.
So exactly right. There's an infinite number. Basically, this is a function, right? So there's an infinite number of scalars.
So it should up to the featurization.
Exactly. Now I will show you in a few slides how to match it exactly. There is a way to match it exactly. In this case, we're using scalars. The scalars are really nice because it's very robust. If you try to match it exactly, it can be a little bit dangerous.
It's not that you're stopping halfway, it's just because of the...
Yeah, so I don't have it on this slide, but if you look in the paper, we did 1 feature, 2 feature, 3 feature, 4 feature, 5 feature, and you can get better and better, and it never ends. Question?
One thing you might want from a method for choosing a consistent model is good generalization.
Yeah.
And it seems like this would be a good setting where you could ask about whether this particular method for choosing a consistent model generalizes well. You could pick a particular featurization, make sure it matches on those, and then ask, does it match better on things on which I didn't?
Yeah.
Compared to other methods.
So what you're bringing up is like how I would compare the 2 physics-based models without any data, right? So I could just compare them as is, then pick whichever one's better, and there's many tools for comparing the physics-based models, and then add data to it. So, or you could choose some intermediate step. But yeah, I think your point is valid, is that these are physics-based models, and there's lots of ways to compare them using any kind of observables you want.
I guess I want to compare 2 different methods for making a physics-based model consistent with.
I see.
You're proposing one.
Yes.
A reasonable one, which is.
I see what you're saying.
Using entropy
Yeah.
as a measure of distance, but I could do something else.
Yes. So actually, that is a topic. Like I said, there's 28 different methods here, and really the problem is that checking generalization is highly system dependent, right? And it's an empirical exercise. What people look at and what I look at is what are the attributes of the model after it's been biased. What's nice about this model is that there's no, in most other methods, you have to have a ensemble of models. So most of the other competing methods, basically, they bank an ensemble of models, and then any kind of average over that ensemble is the maximum entropy version. We sort of did this optimization here to find it directly, whereas most people don't have to do this extra step where they find alpha. They get around that by making an ensemble of models. But we find, people avoid this because they're afraid it's going to be hard to find this alpha. But we find even with quantum dynamics of water, you don't want to do any calculations of quantum dynamics of water. You want to just be running the right model. We can get to it within, maybe 25 iterations. So it's very, very quick convergence. Okay, so I'm just going to move on, and I'd love to have more discussion about this in a minute. So basically, after improving it, so we improve structure, and then I'm looking at dynamics here, and you can see in the dynamics, we get the mechanism from 70 to 1 to 10 to 1. So I didn't bias dynamics. This is a side effect. So this is a way to check whether biasing one property helps the model improve. And then we can see our water diffusivity goes from 0.007 to 0.13. So we drastically improve water diffusivity, we drastically improve the mechanism, all from changing the structure. And that shows you, if you start with a physics-based model, right? If you improve it in one way, a lot of times because the physics is in there, it improves in other ways. Now, this method is not, I don't want to present this as competing with dispersion corrections. So we actually went back and put it with the dispersion-corrected model. So now we have dispersion-corrected DFT with our method. And you can see now we get nearly perfect agreement. And then these actually improve by quite a bit in the other. So this is here. This is what I showed you in the previous slides. And then now here we are with the improvement. So it's not something that's like competing with other physics-based improvements, right? There's other sort of empirical corrections people make to physics-based models, like the dispersion correction in DFT, and this works just fine with those. And you can get something even better than DFT with dispersion corrected. Okay, so we started with a sort of reasonable guess, BLIP DFT, and then we minimally changed it to match experimental data. And I put here, rather than implicitly choosing model assumptions, there's sort of a dark art in quantum dynamics of water about raising the temperature, choosing this pseudopotential, choosing this basis set, starting your configuration just right. So this is sort of a way to make it explicit. Question?
What did you change?
What did we change? We added a minimal bias to the potential energy.
Which was a function of which thing?
It was a function of a function of the structure factor we calculated from X-ray synchrotron experiments. So on this slide, what we biased was this observable measurement, which we obtained from experiments.
But the term that you added depended on?
The observable only.
Did you consider changing the observables?
Did we consider changing the observables? No, we take the experimental observables to be ground truth. So we don't consider changing other observables. Okay.
Not the value of the observables, but the things that it's a function of.
Right, so the things that it's a function of, we believe it to be a function of the underlying probability distribution, right? That's the most fundamental way of defining the observable, so that's what we change is the underlying probability distribution. Your question, Frank?
It was the same question.
Oh, okay.
Yeah.
Sorry,
Okay.
can I ask?
Yeah.
So you do this magic for specific conditions. The problem is with water that whenever you change temperature, like not very much, you change the whole properties a lot.
Uh-huh.
And it's again become, because of the quantum effects, if you want to do mathematically correct, like you do the right by classical system plus
Yeah.
one, but you need to change potential energy source and the kinetic energy term. You can't just mathematically change potential energies and change temperatures and get correct result. So what will happen if now you do this fitting at an experimental temperature and then you change the temperature a little bit?
So, yeah. I will give you two answers to this question. The first answer is that because we've shown that this is the smallest change you can make, the ability for the underlying water model to predict changes in temperature is sort of intact. So if the model was showing changes in temperature correctly before, we haven't changed that. Now, you're right, is that maybe our bias is completely wrong at different state points, and that will be the next topic of my talk. So great point. Now, I would just mention here is that we sort of have a general approach. So you can do arbitrary numbers of scalars, and you can do nonlinear function marginals. Okay, so if you have a collective variable, you want to change the free energy. That's the same thing as you have a marginal probability of a nonlinear function, and you want to change it to match. So, we have a review and molecular simulation out this year. We have implementation in Plumed, which is a common MD method. We also have an implementation in TensorFlow and an implementation in HUMD-Blue. And so you can use it in many simulation engines from quantum to classical. We use it usually in classical. I just like the quantum water example because it sounds really hard. Like it sounds like a really hard model to fix. So. All right. So this has been used in many approaches now. So Giovanni Busi extended it to deal with uncertainty in experimental data. So obviously, if you take an experimental measure, you're going to have uncertainty. Thomas de Lafarge did this with coarse graining. So if you have a coarse grain model and you want to put some knowledge back into the coarse grain model afterwards, this is a way to bias your coarse grain model to match experimental observables. In the review paper, we show how you can use it in MPT ensemble. Glenn Hockey at NYU has done this with ultra coarse graining. So basically, you want to replicate a mean field that is like an environment. So you can actually represent that mean field as a series of these experimental biases rather than trying to compute some mean field, from traditional sort of mean field computation when you have a very fine model and you try to coarse grain it out. We can actually build a mean field of sort of knowledge. And then you can use it with enhanced sampling we showed. You can do probabilities. I'll talk about that in just a second here. And then we use it to do inferring peptide self-assembly structure from NMR. Okay. So I just want to talk on this. So one of the tasks we can do with this is that if you want to change a collective variable to have a specific free energy. Okay. So if people typically, so like fitting like cryo-EM data, or people like trying to fix some kind of collective variable to match some observable. So like the RDF, the radial distribution function, is an example of a probability distribution. You might want to fix that directly rather than doing these features. What people do a lot of times is they just sort of add in the knowledge as a bias, right? So like in cryo-EM, you just put the electron density directly into the potential energy, and then you just sort of scale how strong it is, and that creates this red line. So if this is my underlying model in blue, and I add where I want things to look in green, you don't end up with this distribution. You end up with the product of these two distributions. That's the red. We have this method that allows you to get exactly. So you basically take your original blue model and then you reshape its collective variable to match your targeted free energy. So in probability, this just means I have some nonlinear function of my probability distribution, or an observable with a probability distribution, and that's a marginal. I want to change that marginal to match some known marginal. So this is a way you can do that. So it's built on metadynamics. So this is metadynamics. Metadynamics flattens things. So we just sort of said, hey, if you can flatten it with metadynamics, can you make it into any arbitrary shape? So that was the idea. So I don't want to get too deep into it, but just basically, we did scalars. This is an infinite number of scalars, right? Or you can think about it as functions instead of scalars. Okay, so then what I just described to you was how do we end up now with this model. I think I have I'll show this picture, okay? So after doing EDS, that's what we call our method. So you start here, you disagree with experiments, and then you now agree with experiments exactly. But to achieve that, you have put in an n-body potential, because we have the observable now in our potential energy, and observables are often really nasty, right? Like NMR, computing NMR chemical shifts is not a nice function, so that would be a really bad thing to have in your potential. So what we want to do is we want to have a way to then go back to a two-body potential, and then hopefully it will stay on this line of agreeing with experiments. So the way I'm going to show you in just a moment here is how do we go back from the n-body to the two-body while trying to maintain our agreement with the experiments. Of course, you could just directly fit the two-body to experimental data. And that's what people do. People try to change potentials to match whatever observables they want. What's nice, I'll show you some nice properties of this method, but if you start with a maximum entropy bias, you sort of have arrived at the right answer for the probability distribution, and then you just need to find the potential energy that gives you that probability distribution. So it's a little bit of an easier problem than trying to find the potential energy that gives you the probability distribution that gives you the observable. You sort of save yourself a step here. So I'll just show you a little bit what that means. So let's go back here. So here we go. Here's our problem, is that we want to minimize this disagreement. So now we don't have a constraint. Okay, so in this setting, I just want to change. I want to make my model agree with the data, and I don't care if it's one of many degenerate models. So we need the gradient. So this gradient can be computed through a very large bookkeeping process that changes every time you change your potential. So every time you change your potential, you need to run a new integration to estimate this expression. And this expression basically says, go to your potential energy, take the derivative with respect to every term in your potential energy, make a giant matrix of those terms, and then get their averages over a simulation. And then as soon as you change one, you need to redo the simulation because you changed your probability distribution. It's a nightmare. People do it. That's how force fields are developed, but it's really difficult. Okay, so this is the idea. Okay, so here's what we're going to do, is that rather than try to match directly, we're going to start with our maxent probability distribution. So we did what I just described before. And now we're going to find the potential energy that is close as possible to our maximum entropy ensemble. So instead of going directly from here, to some two-body potential, we're going to take a detour to the maxent and then stay as close as possible while changing the probability distribution. So here, n-body, here, two-body, make them as close as possible. Now what's wonderful about this term is that if we do a simulation from the maximum entropy method, and we have to do a simulation to find alpha, we have to do a simulation, then every observation in that simulation is sampled according to the maximum entropy distribution. So this is 1, and this is 1, so it becomes just a sum of logs of your potential energy. So rather than having this nasty thing here, all we have to do is just sum over our observed conformations, and that gives us directly the KL divergence, and then we just minimize it. So we don't need to run a bunch of simulations. We don't need to do anything. We can just reweight it. Now, whenever people hear reweighting, you think, oh my gosh, you're going to have a bunch of zeros, right? But the thing is, we already were at the right distribution, right? We already have all the conformations that we know contribute to the probability distribution, so we don't have to worry about any kind of reweighting issues. Okay, so how do you actually compute this? You can use a derivative-free optimization. You can estimate the gradient with just basically, you just make a bunch of, you can do bookkeeping. You can just do all the derivatives of the potential energy and then reweight them. You can use these derivative-free methods where you approximate the gradient by sampling in different directions. I'm going to just sort of skip over this in the interest of time, but you can, this is a very straightforward method here to just basically minimize this expression by changing your potential energy. You can even use force matching if you want to assume a basis set. So you could take any of the many successful coarse graining methods and apply it here.
Sorry.
Yeah?
Your thing about it's 1 both times, I mean, like if I have a Gaussian and I sample from it,
Yeah.
I'm sampling they're like unweight. If I do some unweighting procedure, I can think of them as all having like good samples, but that doesn't mean the density is going to be.
So if you were to take, right, so I'm basically taking the expectation of this expression here, right?
Yeah, but I don't see why P doesn't go away in the denominator, just because that's simple.
Because each one of these frames is an equal probability. So it doesn't disappear, but down here, because we're minimizing, maximizing, it's just a constant. Right, so it's equal for each frame.
Okay. Well, you're going to try to maximize the Q?
I have to think about this. Trying to minimize Q.
But Q, you're optimizing Q.
Yeah, we're optimizing Q. Yeah. I guess that's true, yeah. Thank you for pointing that out. Okay, so anyway, just to summarize, I'm going to skip the results here, but you basically do what we just described in the first part of the talk. Then you randomly perturb your potential to estimate your gradients. And then you update your gradient estimates just using, you can use Atom, you can use any stochastic gradient descent. And what's nice about this method is you can just do one simulation because you already have arrived at the right ensemble, so you don't worry about reweighting artifacts. And it has a uniqueness convexity guarantee from the previous method, right? We know that we can get to the right maximum entropy ensemble. There was a uniqueness guarantee there. And then now we're fitting a distribution. Now, I don't know, maybe there's not a uniqueness guarantee when you have a distribution to a distribution, but I think that there might be something like that. Probably not, though. We need to work on that. But at least getting to maxent, you have a convexity uniqueness guarantee. And I think it's fundamentally an easier problem to fit a known distribution than to fit the ensemble average of the observables. Okay, so I'm just going to skip ahead here. So, what time am I supposed to be doing questions?
Still have 10 minutes.
10 minutes. 12 minutes, okay. So I will quickly, I want to get to this active learning part, so I'll just kind of skip over this. But I'll just mention this is that, how do you actually get the observable, right? Sometimes it's not obvious how to connect an observable from a simulation with an experiment. So one thing you can do is use a deep learning method. So I'll just mention we've done this for NMR. So NMR is a really commonly used method to calculate from a simulation, NMR chemical shifts. So we have used a graph convolutional neural network to calculate NMR chemical shifts. And what's nice about this is that it's differentiable, and we can put it into we have a TensorFlow MD engine. And so we can compute NMR there. And this is a great observable device because it's a really direct measurement in an experiment. And so basically, I'm just going to skip through this real quick, but this is what our graph convolutions look like. So here is something I'm trying to predict the chemical shift on. And it's connected to all of these different atoms. And we have explored what we decide to connect. So it's connected here to both things that has a covalent bond, and it's connected to nearest neighbors. So I'll just skip through and show you is that we looked at basically, if we connect only to bonds, our performance here. So we want this performance to lie on the line. So this is basically what is the measured and what is the predicted. So we want this to be all on the same line. If we only look at bonds, we get a reasonable fit. But then if we start looking at larger neighbors, you can see that we couldn't distinguish between these chemical shifts. Now we get spread. If we add non-bonded neighbors and if we add distances, so things start to spread out. So by adding in features like who we're near and if they're a non-bonded neighbor or a bounded neighbor and how far the distance is, we can do a really good job of predicting NMR chemical shift. I'll just skip through. So we did this with small molecules, so you can predict small molecules and proteins in the same model. Here's our results on 25,000 in our validation step. And our model's okay. It gets 0.26 as our mean squared error, but state of the art is down to like 0.1 or 0.13. But what's nice is that we didn't have to actually do a lot of hand engineering features. This just learned all of it and then works on metabolites. Yeah?
Is there an is there like a statistical error in the measurement? There's a problem of matching the to be exactly on the line.
Yeah, so I think you can see from these other methods where people worked on them for years, like 0.1 is sort of the noise. Right? But then there's another question that I didn't talk about. I'm just going to skip through this. But basically, you're taking X-ray crystal structures and connecting them with NMR measurements. X-ray crystal structures are not exact, they're not the same experiment as the NMR. So we don't expect them to ever perfectly agree.
So this is solution NMR?
Yes, this is solution NMR. But the way people fit these models is they need to have an atomic structure to start with. And so rather than fit to what people get out of Explore from the data, they fit to re-reference crystallographic data with NMR solution data. Okay, I'd love to talk more about it. So I'll just mention here that we have developed a TensorFlow HumDBlue MD plugin. So a lot of the work I've just described here is only possible by having this. So we can basically write out Python kernels that end up being really efficient GPU calculations. So you can do things like having your force field defined in Python TensorFlow. You can define arbitrary collective variables in Python TensorFlow and get automatic differentiation. So a nice example would be like if you want to compute a Fourier transform of your radial distribution function. That's a hard thing to implement by hand, but it's just a couple lines in TensorFlow, and you can do derivatives on it. So you can do biasing in Fourier space, which is kind of cool. And so I'll just mention that it says here, and you can do coarse graining, you can do free energy methods, and it's all GPU to GPU, so it's a very efficient way to do machine learning and molecular dynamics. Okay, so I just wanted to get to my last part to talk a little bit about active learning. So I just described basically how we can take a physics-based model, improve it with data, and then, if necessary, change the underlying parameters. Okay, but then what about choosing which experiment to do next? So I'm going to talk about peptides here. So peptides are a nice chemical system because we don't have to debate about how to represent chemical structures. We don't have to debate about if Smiles is good or Selfies is better. Is Inchy the best? So peptides are represented with 20 amino acids, and they have a really wide variety of chemical structures. So basically, these are the 20 amino acids, and they have different side chains. So the right side is the backbone that you're building up, and the left side is your side chain. So you can make charged, aromatic, nonpolar, polar peptides, and they're all represented as linear sequences. So you can write them down. This is a peptide, this is a peptide, this is a peptide. So you can write down a chemical structure as just a linear, as just a string. And there's 10 to the 30 possible peptides. It's just a benchmark calculation. So there's a lot of design space here, and you can make things which are accomplish a wide variety of functions. So people can make peptides that are antiviral, peptides that are soluble or insoluble. This is just something you can measure of them. You can make peptides that bind to proteins. You can make HIV drugs. You can make MRSA drugs. You can make them kill red blood cells. You can make them anti-cancer. So people have developed data sets for a huge variety of peptides. And so we have here basically a number of tasks with peptides. And so I've been really struck the last, year or so with the idea of doing active learning and meta learning at the same time. Okay, so active learning is choosing which experiment to do. Meta learning is learning general knowledge across a wide space of tasks. So this is a great system where we can actually try to learn meta knowledge by looking at different tasks. So we have peptides, so the same data, and you can do different tasks with it. So these are the different tasks we can do with peptides. So can we learn a very efficient way, sort of few-shot learning, can we learn a way to do active learning on this data for a new task? So if someone said, hey, I want to design a peptide that is optically chiral, then I could use my methods designed on these tasks to be as efficient as possible on the new task. Okay, so I'll just mention here, so we do a very simple neural network. So this is based on some of our past work on convolutional or on motif finding. So we basically take our peptides, we make them into one-hot vectors, we put them through a convolutional filter, and that just finds motifs, so one-dimensional patterns in our peptide sequence. And then we also separately put in counts of the peptides, and we concatenate that down here. And then we just do a pooling, and then we just have a couple dense layers, and then we can predict a classification. So this is sort of a general convolutional neural network that takes in a peptide and can predict the class of the peptide. Okay, so we're not trying to predict all the classes at once. This is just a binary classifier for any task. Okay, so there's this like new manifold learning method called UMAP, and they made like a really compelling YouTube video, so I thought I'd throw my data through it. And I just wanted to show whether or not we can learn. Okay, so here is my data, and I've basically taken the strings and represented them as like a 4,000 dimensional vector because the longest string is 200 and there's 20 different letters. And then I did manifold learning on this, what did I say, 4,000 dimensional space. And I just wanted to show, is there a difference between things which are soluble and insoluble, right? And so yes, there is a difference between things which are soluble and insoluble. So I think this is a really nice thing to see, is that a neural network could actually succeed on this data because there is a difference in this manifold between these two data sets. So obviously there's some, overlap, but in general, we should be able to distinguish between something that's soluble and insoluble. And this is another one for antibacterial peptides, so there is indeed a difference between non-antibacterial and antibacterial peptides. Okay. So just if we take the neural network, we do standard training. This one we did this is epoch. We did, I think, 100 epoch. And we did 100 iterations per epoch, and just showing you that we can learn. So this is on a withheld data set. So if I go to the cancer one, I can be 25% accuracy. By the way, this loss is 1 minus accuracy. So I'm going to be 25% accurate on predicting if a new peptide is anti-cancer. Okay, or we can go to antibacterial, and we can get down to 20%. And this is just showing you sort of the spread of it. So it's possible to learn on these data sets. So I'm not going to get into trying to find the best model for these, but I want to find a general model. Okay, so let's, I have 3 minutes left. Okay, so some active learning. So first of all, what is active learning? Active learning is choosing which peptide we want to test next. Okay, so we want to find a strategy for which peptide to test next. And in our case, we're just basically have a fixed horizon. We're going to do 10 experiments or 50 experiments, and we want to find out, can we learn as efficiently as possible? So which 10 peptides will give us the best model performance? So in sort of a real setting, this is if I want to do 10 experiments, what are the best 10 experiments to do? So if we do sort of a standard active learning method, that is we find which peptide has the most uncertainty, I'm showing you here basically the blue traces are the active learning approach. The gray is what happened if we trained on all the data for a long time. Okay, so on the antibacterial, if we train on the data for a long time, we get a 0.33 loss, which is 0.77 accuracy. And you can see that if we do active learning strategies, we don't get anywhere near that. And though we have random choice, so random choice is the green dashed line, it's the same. So that is, if we choose randomly or use uncertainty minimization, we get the same answer. So no matter what we do, we sort of get the same answer for just 10 peptides. Okay, so basically, uncertainty minimization doesn't work for designing peptides with active learning. Okay, so then we can use query by committee. I'll just mention we basically scramble our hyperparameters and make an ensemble of models. Then we look for disagreement in the models, and that's our choice. Okay, this one works a little bit better in some cases. So like this is anti-cancer. You can see that in some cases we are able to train a little bit better than random choice. So here and here, sometimes we can get a little bit better than random choice, but generally it's not that great. So I think the soluble is a good example. But overall, 0.5 is random choice. So we're basically after 10 experiments, we're able to get a little bit better than random choice. But query by committee overall is it's not that great. Okay, so here's what we can do active learning. So meta learning. This is where we can do meta learning. So meta learning is where we basically take our 11 data sets and we hold one of them aside. And on the 10 data sets, we do training on this process. So basically we train a model k times, and we see what is our loss after k times, and then we find out what are the parameters that gave us that loss. We can do backprop to find out what was the initial distribution that we started with and optimize that. So we're changing the hyperparameters to optimize our loss after k steps. So we have to sample across tasks. I think there should be a sum here. So we sample across different tasks, and we see what is the best hyperparameters we can get. Okay, so here's so we go back to the uncertainty minimization. So like I showed you, uncertainty minimization is a terrible process. But if we do this meta-learning, so here, we never saw antibacterial peptides before, but we had done meta-learning where we optimized our hyperparameters to learn as quickly as possible on new peptide data sets. You can see that we start with very good one-shot performance. This is after one training iteration. So our one-shot performance is actually really good. So we have 0.3. So we have 0.7 accuracy after seeing one peptide example. And then we don't seem to improve that much. Okay, but we're still better than if we trained on all the data. So why are we better than if we trained on all the data? Because this is withheld data. And the one that trained on all the data, can only generalize so well. But here we actually started with optimal hyperparameters, and so we get a really good fit. Now we go to other cases, and we can actually yes.
It's really just the hyperparameters you're transferring across.
So hyperparameters, when I say that, it means it includes the initial distribution of parameters. The initial parameters.
The initialization of the network.
Yes, exactly.
Anything about post-training parameters.
Correct. Nothing else. It's just initials in this example. Yes. I mean, so this is equivalent to few-shot learning, right? You're just basically training your initial parameters to be as efficient as possible. Now, what's interesting about this, and I think we're supposed to submit this on Friday, but I'm still not so excited about it. But there's still some cases where we don't do as well. So in general, this is much better than random choice, and it's much better than not doing meta-learning. But there are certain systems where we just, for some reason, don't do as well. But in general, we actually have really good low-shot performance, and we do, in certain cases, see very good training after 10 experiments. And I'll just highlight a couple. So in general, all of them are very good. But the gray line is we're training on all the data. So if we're at the gray line or below, it's great. There are a couple examples. So this one, the training is just terrible. It just basically does as well as random. This one is a little bit above the control, and then this one is a weird one. So all of these examples are biological except for solubility. So if you take solubility out of your training data and then go back and try to predict solubility, I think you're overfitting. So I think that explains why this one is such a tough one if you take out. So we're adding another data set that's another physical property so that we can sort of have more general tasks. But you have to be really careful about overfitting to biological tasks. So that's why we have the hemolytic, and these things are binding to proteins, so it's not sort of a general biological observable, because antibacterial means you have to be soluble, you have to be available, you have to be able to penetrate the cell, but these protein bindings are a little bit more narrow. But essentially, we can get very good low-shot performance, and we can get good active learning when we do this process. Yeah?
And your gray line is not trained with the optimized hyperparameter.
Correct.
Some other random hyperparameter.
Just random, I think glorit, whatever it's called, random initialization. Yeah.
And so if you trained with all the data with the optimized hyperparameter,
we didn't.
Presumably it would be much better.
It's presumably much better. We haven't done that. Yeah. So, this is, I think, a really exciting result for us, because it shows us that in peptide space, we can learn some kind of general knowledge about making active peptides. I think the zero-shot performance is really surprising, or the one-shot performance is surprising, because it means that there's something about a peptide being active, and it might actually be to do with the solubility, right? Like, you need to be soluble to do anything. But there's something about, intrinsically about a peptide being good at these tasks that we can get from one training iteration. And I think we need to explore a little bit more about the acquisition function, like how we choose which experiment to do. We're just doing uncertainty minimization and query by committee, but you can obviously do Bayesian optimization and have very sophisticated acquisition functions. But for me, this is like our most exciting work, and this is what I want to learn more about at this workshop, is that can we learn general active learning strategies on classes of molecules or materials? Okay. So, with that, I'd like to thank the group, everybody who contributed to this work. Megishri is here, and we do some work on course grading, and she's excited about that. And then I'll thank our funding sources. So this has been funded through 2 NSF awards, and then we have an NRT on data science, and we do some augmented reality work as well. So with that, I'd be happy to take any questions. Thank you.